Hello, Thomas.
Hey, Luca, how are you?
I'm good and good. I'm noticing that we have names under our faces that say Lightning AI and Thunder on the other side. It's pretty. Yeah.
Yeah, you
I am
started the
Luca and you're
Lightning
Thomas.
AI, so I switched to Thunder a couple of episodes ago.
See, I didn't even notice. So we haven't been speaking. Well, we have been speaking a lot, but not on this channel for a couple of weeks now.
Right.
Yeah. And we've been busy though, right? And by the way, we're ready to take a little break for the holidays. But what has kept us busy was, we started scratching our heads. We talked about, yeah, exactly. We talked about memory consumption, right? So we were looking at Llama on the Hugging Face repository, but that's valid for any implementation. And we saw that, yeah, of course, when you do a forward, then you do a backward. You want to eventually trade some, spend more compute to use less memory, and instead of saving all the intermediate tensor in the forward to then use them in the backward because you need them for the back propagation, you can throw away some intermediates here and there and just save the ones that will allow you to just rerun a small part of the graph in the backward, in forward, and then have the intermediates there locally. So reallocate some memory for the intermediates, actually recompute, use them from backward, throw them away, and do it eventually block by block and use a lot less peak memory. Because ultimately, if your peak memory goes over, you can't train anything. So it's better
Right.
to take a bit more time to compute a bit more, but still be able to train things. And this is used. This is not something that is like a no-no. It's actually used pretty widely, and this is what we wanted to do. But when we looked at the plot, it looked like we weren't really recomputing at necessarily along the way, and we were still seeing kind of a memory peak. And so we went back and say, okay, what is going on? And the first thing to do when you don't know what's going on is build the tools to know what's going on, right? Instead of starting to throw the solution, a possible solution at a problem, but it's not the right solution.
Yeah.
So now this episode will be about what we built and what we found out in order to understand how your model uses memory. And it's a big deal because in forward, you can stop things, blah, blah, blah. But in the backward usually just happens, right? And you don't have a lot of control in that. So how do you like figure out what's going on? Anyway, this episode is all about that.
Yeah. And obviously, it's the thing I like to say. It's not optimization if you don't measure. So
Yep,
we'll get a lot of tape measure to work with.
exactly.
But first,
And
some
that,
happy
no, no, go
news.
ahead. Yeah,
No,
no,
you
go ahead.
want the
No. I say we'll see how awesome Thunder is because it lets us inspect the heck out of the problem. And so I'm very excited for this episode. But first, as you were like introducing, I just pushed the button on the Lightning 2.5 release. So PyTorch Lightning has been released, the new version. So thanks to all the contributors out there. There's a page that you can go to, like on GitHub. You go on GitHub, PyTorch Lightning, you go to releases, and you see the 2.5 release. There's a bunch of things. One of the interesting things is that we show how to use Torch.io for quantization, distributed tensor to do distributed tensor, and Torch compile in PyTorch Lightning and Fabric, and also and the same mechanism as you probably got it if you're an attentive listener can be applied to Thunder, but we'll show it in the near future.
yeah.
So there will be a way to use the compiler within PyTorch Lightning and Fabric very naturally through the same mechanism. And the other thing is that we went back into PyTorch Lightning and reviewed everything that pertains to internal counters. That's a big deal because when you train on large clusters and something goes down because things happen like that, you need to resume exactly at the same place. And we noticed that there were some slight inconsistencies in some edge cases. So we went back, added a ton of tests that would test what happens if you break at every point in the loops that PyTorch Lightning handles, so that you have the exact same history of things, whether you blocked, you stopped or not stopped. And so this was a work that took a couple of weeks to go in the ins and outs, because PyTorch Lightning has a lot of callbacks interacting together. So it's a thing, and the learning rate scheduler. But I'm really happy that it's not that it wasn't working before, but now we really hardened that part because it's becoming more and more important in Gen AI times. So, but now this, it's enough with this. Please, Thomas, show us the magic.
Yeah. So maybe we start at the basics again.
Yep.
So let me share my my window here with the Thunder Sessions Studio. The thing I like to do.
That you can find, of course, in.
Yeah, I'm not as good about updating this every week. I should.
You will find.
Yeah. So let's have Thunder and Torch, and because we like graphics, we also have Matplotlib, and in particular PyPlot. And you can tell that I'm not a huge friend of the abbreviations that people do. Mm-hmm. But we wanted to talk about memory, about not saving everything and recomputing instead. And so the name for this is, confusingly or not, checkpointing, or if you want to, activation checkpointing. Mm-hmm. And so let's import Torch utils checkpoint. Oh, and I should put this to code.
Yeah, it's a bit confusing because usually checkpoints are what you save with the weights and stuff, and the memory people have called it checkpoint, which is totally fine. You kind of save things for backward, but us mere mortals, will think about that as throwing away things for backward, because we kind of assume things are saved for backward. So it's kind of a misnomer in my point of view.
The other funny thing, if you want, is that for some reason I can't find the module that does the checkpointing in PyTorch. It's not in the Torch utils checkpoint, at least. So let's just do our own little wrapper here. So super init is what you always want to call, and then just set the module to the module that has been passed in, and then the forward is simple enough. We only take positional arcs here, mm-hmm. because that's what the checkpointing function, which is from Torch utils checkpoint, does. So Torch utils checkpoint, and I think the function is called checkpoint too. So self.module args, and use reentrant false. This is like a silly thing, but it will, like, does it say? No. It will keep us from getting funny error messages. So so this is our warnings. So there's a deprecation warning that if you don't specify it, you need to in a bit. But so let's work on the GPU, and I've chosen
our beloved L40.
Right, and so let's use the GPU too. So and we want to have a simple model for demonstration purposes. So I'll just do a little MLP here with Torch and then Linear. Let's say to a small number, we will have lots of bottlenecks here. And then a relo. And now comes the particular thing. Now I'll do a whole tower of things, and I'll wrap each of them in the checkpoint. So when you have a transformer module, the typical thing is to wrap each block in a checkpoint. But so here we do this for a little.
Yeah. So you have a attention MLP. That's a block plus normalization, and that's a block. And so you would want to checkpoint what is in between blocks and basically not keep an intermediate from within. But you can also apply different strategies, of course. And here we're kind of simulating that by having a linear relo linear as a block, or linear relo. And that's your block there.
Yeah, I mean, it's a very arbitrary thing, right?
Of course, yeah.
And let's go back from 16 to 1024. Yeah, and that's our model. And let's have some inputs too. And I'm not that sophisticated, and I'll just use requires gradient. Maybe we wouldn't need that, but now let's have it. Okay, so yeah, almost works. So checkpoint got 2 arguments. Why did it get 2 arguments?
What was the error message?
Checkpoint init takes 1 positional argument, but 2 were given. I think, yeah, I just need to count the underscores.
Okay.
I misnamed the init here.
Right.
Okay, so awesome module here. Can we run it? So res is imps, and then we want to know that the backward also works. So we'll just do res sum backward, and this works. Surprisingly, not surprisingly. But so the next thing we want to do is we want to thunder JIT it. So jm is thunder JIT m, and for reasons that will become more obvious later than we'll discuss, I'll just do executors nothing here. And we can do it. Do you want first the non-checkpoint version or the checkpointed one?
Let's do the non.
Okay, so I can manually force the disablement by saying enable. I think we had this right. Saved for
backwards, yeah.
Recomputation equals false, and this will. And I'm on a development branch of Thunder that's associated with a PR regarding the checkpointing. So it's brand new what you get here. So let's have this, and now we can run the Thunder module. Yeah, and that's the demo. And it's not even the Thunder module here. I need to the JM. That's the demo. That's not terribly interesting. So what we can do, and we did this last time, I think we had this callback and the debug transform. So let's do this. So we need to have a thing that gives us the memory use. So we can have the callback, and it gets args and quarks and the bound symbol.
Yeah, in a nutshell, the debug transform allows us to call a callback or whatever bsims, and so we can instrument this with a callback that will tell us memory allocated, so we can get an idea of what happens as we progress through the trace. And see how much memory we're consuming. which is level 0 of what we want to do. And we did it the last time.
Right.
But now we'll see how much deeper we can go.
So we can do this here. And it will return a string and the debug transform. So JM Thunder def utils. Oh, I need to import that, right? Import Thunder def utils debug transform, and then I can use the debug execution trace, and I need to add my Thunder module here, and then the post callback is my post callback function. Okay, so we have this now, and what this thing does is it will insert this, and now I can inspect it in the last traces. So if I go to Thunder last traces, JM, and take the last one, you see that it prints the memory that is allocated, and it does so after each symbol. And for technical reasons, there's the debug thing that calls our callback. And it's all in as a trace transform, we have it there, and it modifies the bound symbol. But so the trick is that we can also do this on the last backward traces. And there we also have this.
Pretty flat. It looks pretty flat.
Yeah. But if you look, yeah, it like actually decreases.
It tapers, yes.
Yes. Oh, here's the thing that I forgot. I wanted to have this like checkpoint here. Where's the? I think I made a little mess here from the brackets. And I didn't want to have one of them. I wanted to have a whole bunch of them.
Oh, of course, yeah. Sorry.
I don't need the index for this in range. Yeah, let's do 10 of them. Okay, but so looking at this and scrolling like this, you will get the headache pretty soon. So we do what we shouldn't really do, but we'll do some parsing here. So let's take the string representation and split it by the lines. And so for L in the strings, and if
memory in, yeah.
Memory allocated in the line.
Yep.
And so we just have the memory allocated lines, and now we need to take it apart. Let's use regular expressions. And we can just say read.sub, and we want to have the anything before the equal sign, and oh, this was too much. What did I do?
You want everything after, right? The equal?
Well, but I was going to substitute everything before.
Oh, okay, substitute. Yeah.
Blank.
Oh, yeah.
But so apparently.
Sub, yeah.
apparently this is a bit too much, so I need to escape the, no?
Nope. It's very eager.
Yeah, but why? Do you? Oh, I know why. It's very funny. You do the pattern first, the line last.
Oh, it would have taken
Yeah,
me a
this is
while.
the
I
pros
never used
doing
this.
it.
Yeah.
So yeah, so we can parse the last
Awesome.
thing, and if we want to make good use of it as a list of numbers, we don't do lists, right? We do torch stances. So this will be the memory allocated. And so we can plot that, right? Plot memory allocated. And we see, it like decreases. And what happens is that we start with very high memory allocation because there's lots of things that have been saved for the backward. And then all these get consumed over time. And that was the picture that you drew, right? Where there was the mountain.
Yeah.
But so if
exactly. So this is just to make sure that we're clear. The forward will be the slope, the climbing slope of the mountain. And what you're seeing here is the decreasing slope because you have everything up to the loss, and then you start your backward. And as you consume your intermediates, you deallocate them. And so that's why the memory is decreasing. So it's the right side of the mountain that we drew the last time.
We could plot the the forward here too, but now I need to do torch cut allocated forward memory allocated, and I need to get my brackets right. And you see this part here, the forward, and this part here is the backward, right? And, and so now we can do the activation checkpointing. And if we just set this to true, or it's also enabled automatically, we can just comment it out. And now it will recompute the bits that it needs. And we can like see.
Ooh, look at that.
Yeah, so what happens is here's the forward, and it doesn't.
Yeah, let's stop on the forward. Yeah, let's stop on the forward for a second, because this is interesting as well, right? In the forward, you don't see something climbing. You see something peaking and then going back. Why? Because you're basically throwing away all the intermediates that you create in that argument of checkpoint.
Yeah, and what I did here, of course, is that the activation here at the time where we checkpoint, that is relatively
it's super small. Yeah.
And then there's the larger part, and those are these peaks, right?
Exactly. So you get to the loss, and then you compute the backward, but then you go up again, recompute, and then allocate the intermediates just for this block, and then deallocate and so on. So if you look at the y-axis, here we're going up to 40 as a peak on the y-axis.
Oh, yeah.
As in memory.
40 megabytes, right?
Yeah, what was it before? I can't remember.
Yeah, if you can't remember, we have to recompute it.
yeah, just interesting, I think. Yeah, re-enabled for computation.
And we need to set it to false, right?
Exactly.
And this exaggerates things a bit because for technical... Oh, no, it doesn't even. So I thought it did, but...
It was 40, it's 80. It's twice as
80.
much.
Yeah, so obviously that depends a lot on what's going on here. But yeah, so if we we now go back here and re-enable it. Yeah, so
Nice.
this is nice, and we actually like get it on the as annotations to the trace, and so we can see after each command like what's going on. The other thing we could do is, well, we can do this by inspecting things. And so this is also very interesting. So there's, if we import from Thunder examine, and it could be DevTools really too, if we want to.
Yeah.
But so there's a memory calculation module.
Yeah.
And,
so what do you mean by inspecting? Means, doesn't mean that we don't even have to compute.
Yeah. So what this has is a function called get alloc memory, and so this will give us maxmem and some information that is pretensor. But here we also get we pass in our trace, so thunder last backward traces of JM and the last one. And now I made something, a little extra parameter that is called annotate. And this function has been coded by an NVIDIA colleague, Yan Wang, which is like a great thing. It keeps track of aliases where you have views into tensors that don't own particular memory, and then it only goes out of memory when all go out of memory. So there's some trickery in there. But basically, it goes through the code for us. And now all I did was when you requested to annotate, you also get this on the last backward traces. You get an annotation for it, and so we can see this here that it says memory after the next operation is this and that much many gigabytes, and so we can also extract that.
Yeah, let me go back to this point. So basically what's going on here is that even though before we had to ask CUDA for how much memory it had allocated, right? And this means that you need to have memory on the device in order to inspect it. So if you go out of memory, in order to inspect it, you have to reduce your model to understand why you're going out of memory. Because if it's going out of memory, you will just not have the ability to generate the whole representation because you're going out of memory. So CUDA will tell you, yeah, out of memory, I don't know how much you would have allocated in the future. What we're doing here is slightly different. Like if you create your model, initialize your model on the meta device, and then you trace it with Thunder, then CUDA is not involved. But we know all the shapes of the tensors, well, more or less, or maybe but potentially you can trace your model, right? And just have a feedback on how much memory is going to be allocated by the trace without actually going the full blown annotation. So in theory, in the future, we'll be able to reason about this prior to planning what to do even with checkpointing. So it opens up a lot of possibilities.
So obviously we need to normalize it to the same scale. Yep. But you see that it's the exact same pattern as the actual memory. There's an offset because there's memory from the forward or the allocated model parameters and stuff that is counted in one. And the other thing is that this runs after everything, so it also inserts this line for the debug information. And of course, we don't want that. So in order to make it really comparable, we need to like only keep every second thing. But yes,
Yeah.
so you
Perfect.
see it really
Yeah.
like there's 20 some megabytes that are offset that have been allocated before the forward, and then you see exactly what's going on, right?
Yeah, and we didn't ask CUDA, right? We just inspected the trace to come to this conclusion.
Yeah.
Right.
But so speaking of CUDA, we could ask CUDA, right? So if we wanted to, we can, there's a torch instrumentation for this. And I'm not sure whether this is still like the preferred way because it uses these funny underscore functions. But so we can run this and then we can say JM of the inputs, and then we do the sum, the backward again, and then we can say torch CUDA memory dump snapshot, and we can call it memory snapshot picker. And similar to the profiler, and there is something where you can do memory profiling in the profiler as well, but somehow it is a bit different. So what's up here is that the PyTorch devs built a visualization tool for this, and in order to use it, I can find the file here, memory snapshot, and download it locally. And then I need to call a web page, and it's a funny web page in that it's interactive and you're supposed to upload things, but it will not actually upload the data.
Yeah, it will load it in the browser and that's it.
Right.
Yeah.
And so now I need to find the file and drag it here. And wait a bit. Does it work? It worked in the rehearsal.
Yeah, while you try it again, like I will rehash the concept that we said before with because I think it has many implications. Like, for example, if I initialize my model on Meta device, I could inspect the memory behavior of a model in forward and backward with very high granularity before running it, right? So basically what this means is that I could take a 400 billion parameter model definition and on my laptop understand, or on Studio on the small GPU or even on the CPU, understand what would be the memory behavior of that model as the model executes. So I can identify peaks before I run it. This could also be used in subsequent transforms to say, oh, this is my memory profile. Now, maybe with some heuristic, you chunk it up and you can like strategically place position the checkpoints so that I don't do it manually, but in the future, it could happen automatically. So I know that as I distribute my computation across, I have a very good sense of what memory will do when I run it. Of course, you can only foresee what you capture in the trace. So if there are other allocations that I don't control, I won't see them there. But I think this is really super interesting as a future direction. So what's going on here? There's no...
Yeah, I have no idea, to be honest. So...
you have the one from before?
I have used it before, but I have several browsers, and I usually used it with Firefox.
Yeah.
And sure enough, it's not like in Firefox it loads and it works. Okay.
Nice.
So let's take this apart here a bit. So what we see is that there's like a bunch of things that are pre-allocated. Obviously,
Oh, we're not seeing this. We're not seeing this. You're still sharing
yeah,
the Chrome. Yeah.
I need to
Just
share.
stop sharing and reshare. Yeah. So this is a Firefox only tooling. Yeah, interesting.
Yeah, I don't know if that's a Firefox only tooling, but
Yeah, no, probably not. Maybe Chrome has some added security things that you need to disable in order to run this. I don't know.
so I hope it's the it's the right thing that because it just says Firefox. But yeah, here.
Yeah, here it is.
So what we have is there's a bunch of blobs that are pre-allocated and probably this is some system stuff. The small bits here likely are our model, but obviously if you have like a huge LLM thing, then all these small bits don't really matter.
Yeah.
And then we see this here is the forward. And if you want, you can have for each allocation, here's a traceback where it got allocated.
Mm-hmm.
Now, this is not that interesting because it only says like the line number. It doesn't show the code, which would be super awesome, right? So maybe next time we'll have a tooling that also shows like the exact line that this has been at. But so you see here the forward, which has all these linears, and then you see here the backward, right? And this is exactly the profile that we saw, except that now you already also have like information on the lifetime of each tensor.
Yeah. Okay, so it tracks individual lifetimes with different colors.
Yeah. So this is an awesome tool, of course.
Yeah.
But it would be even more interesting if we could like connect it closer to the source code.
Yeah.
Which is, by the way, one of the things that I think is hugely cool about Thunder. Obviously, I'm biased, but so having the ability to also for the backward, just like show me the program, show me the trace. That is quite a thing, right? Because usually you don't have this information. So what we can do now, if we want to be a bit experimental before Christmas, we could like try to apply these tools to a larger model and see where this leads us. So let's import libgpt and with torch device CUDA, we can use the model. Let's use libgpt model GPT from name. And our favorite one was Llama 3.3 1 billion. And we'll use the bfloat 16 version of it, right? And so the input for this needed to be some string because some tokens. So let's do here 1 and maybe 512 tokens, and it needs to be integer, right?
Yeah.
So it's a bit of a lame thing. Okay, it's not. Yeah, now comes the Llama 3.3. Is it Meta Llama or what is it?
Yeah, let me check it real quick. HT. Oh, it's 3.2, 1 billion. Not 3.3.
Oh, yeah. Yeah, 3.3 is the 7.
Too much. Yeah.
70 billion
70,
models, almost
yeah,
as good as 400. Okay,
yeah, exactly.
so there's our model, and now our model doesn't have checkpointing, I think, right? So
No, it doesn't.
so if we look at the model, it doesn't have checkpointing, so we need to get checkpointing, and so we can do this by, how do we do this? So for I in range 16, we can do model transformer HI, and then checkpoint of M transformer HI.
Nice.
And you want to be somewhat sure that you only run this once, so I'll copy to the instantiation of the model itself. So here,
Amazing.
I have the checkpoint here, and we can try to run Thunder through it. So let's do jm equals thunder.jit of the module, and res is jm of the input. And this will take a moment.
Yep. Of course, in the future, like in a future, right now we're deciding where to checkpoint in the source code with monkey patching kind of the model. In the future, we can easily think about something like, it's a transform, or it's a transform that will first estimate the memory and then decide where to checkpoint. Like possibilities are very, wide.
Yeah, to my mind, like one of the interesting bits would be so it's not trivial because basically you need the forward and the backward, and then you need to make decisions about it. But so one thing I could imagine is that you actually try to have a priority list of where to checkpoint, and then iteratively until you see that it like fits the memory.
Yeah, it's a cool project. If anybody wants to, get into Thunder and play with this, it's a very cool project. Yeah.
So I didn't run the backward yet. So I'm not sure that it will work, but let's try. This should be somewhat faster, and we can see like what the GPU does. Well, it's keeping up pretty well, right?
Yeah.
So far. It's a small model here. It's the 1 billion, and it is a very short thing. But what we can do now, in addition to just watching the memory here, is we can inspect the last backward trace, right? And we can do, and we're too late to actually inspect the thing, but we're not too late to do the estimation, right?
Yep.
So we can do the last backward traces -1, and then Thunder examine memory calculation, get allowed memory of the trace with annotate equals true. Oh, this runs into an error? No. That is terrible. Okay, so let's try to go back in time a bit. Okay, so
Yeah.
this is better. But so the bad news is that very likely, I don't know, we will have to see. If we look at the trace, we see that memory only keeps increasing because we probably...
Well, because the executors was no,
Well,
we
so
didn't
this is
select.
constructed by the transform for execution. The
Yeah.
trouble is that it doesn't include the deletion of the last used, I think.
Oh, I see. Yeah,
So
makes sense.
we can plot the memory because we're like honest people. Um, but
But we're basically not seeing the
it
deletion.
you will not see the deletion, I
And
think.
so as we don't see the deletion of the trace, there's no way for the utility to detect that we're actually deallocating.
Yeah, so it actually tracks it like Python would. If you don't do the deletion, then it keeps it around. So st memory allocated, this
Yeah.
goes up, right?
Yeah, it looks like a Mario level. Okay.
What we can do is that and I'm not sure why the other thing failed. It's just pretty bad. Okay, but so what we can do is we can say del tr is thunder, and this is in a funny place to executors del passes, and I think it actually is there, but we can apply this manually and see if we get... No, we don't get... Oh, we need to...
Yeah.
Yeah,
Yeah, we're not passing LTR there. Yeah. You need to use it.
Yeah, we need to do the estimation.
Yeah. But
I need to remove this
yeah,
printing of the trace. So we want to have this estimation on the del tr.
then you need to use the LTR there. Exactly. Yeah.
And then let's see if that works. And oh, why did I have this here still? But yeah, okay.
Yeah.
And this runs into the assertion error. I don't know why exactly it does. So tr thunder, something it doesn't understand. But let's try it on the initial backward trace, and it still runs into the assertion. So there's a problem there. I'm sorry.
Yeah. No worries.
I tried this with a different model. I think it was the maybe we can try it. Do you know the name of the coding model?
Code Llama
Yeah.
or
Well, stable code completion.
okay.
Is that a name for I can use here?
Let me see.
Yeah, I can.
Nice.
But
Yeah, it's interesting. Of course, needs to be fixed.
yeah. So now you know what I'm going to do.
After the recording. Yeah.
But yeah. So did this have 16 layers? Maybe we should have just said, let's have 4 layers here. Now I'm running out of memory. No. No, what's the... Oh, you can't do this with the... Can I do this with from name or?
The N layer?
Yeah.
Not sure.
So let's do a config lit config. So with the config, I can do it. And with any bit of luck, the config says n layers 4 here. Okay, so and now I run out of memory. No, index 4 out of range. Yeah, this is good, right? This was here. And now let me see if I have done this right. Yeah, this looks pretty reasonable.
Yep.
And so we can actually like skip running the backward and it will still work, hopefully. And now it worked. So on the last trace. And I can...
Yeah, I can remove the del, right?
Yeah, but it will like come back in a bit. So
Aha.
oh, this still only increases, which is curious, right? And it's the back one.
Is it the backward though? Because you put TR, and what is TR? I don't think TR is. Oh yeah, it
It
is.
is the last backward trace. But so should we look at TR? Does it have deletions? Yeah, it has deletions. So apparently, like, because we calculate a whole lot of gradients, things increase, right?
Mm-hmm.
Could be. I don't know.
You could, yeah.
It is a very...
Well, you could compare it with the non-checkpointed one, right?
Yeah, but it's also like not quite the thing I expected it to look like, because I thought that we would get like you can see the 4 with a bit of imagination. You can see the 4 blocks here, right?
Yeah, exactly.
I just don't know why we don't see a drop in the memory, because it should like it should drop at some point.
Yeah.
But yeah, so we could try to go back. No, we need to figure it out, I think.
Yeah, I think what we can do.
I think what we're seeing is that this is very short. So if I do this like 8192, so the reason why I think that might be part of the reason is that if you have like very short things, but the gradient will be for the
Yeah, the
entire
gradients dominate. Yeah, for sure.
thing, then the gradients dominate everything.
Yeah.
Uh, so let's try with a slightly larger thing. Basically, we now scale these bumps,
Yeah.
and the endpoint will be not scaled as much. Now I actually ran the backward, which I wouldn't need to. But yeah, so
Yeah.
now we can
That's
see
it.
it, and
It's
so
amazing. Yeah.
these little crowns are, if you want this is the dragon tail that
And
I
this is
wanted
4
to
blocks,
say
right?
about,
So you
right?
selected 4 blocks, right?
Yeah, so those are
In
four
the
blocks. And what we see here, in addition, like these bits, these are things that we still need to work on. And that we need to work on it, we can see if we compare like previous traces. And now we are back at the LTR bits. So if we do this,
previous traces through the transformation. So right now you're saying, let's not take the last backward trace after all the transformations. Let's go back in time to what the backward trace is,
right,
re-add the delts in there, and then see how it would have been if we skipped the last few, like transform
right.
or execution, for example.
So if we go before the transform for execution, we see
Oh,
that
wow.
it's
Yeah.
like a much more tame pattern, and it's
Yeah.
like a lot lower here.
Yep.
And
Yep.
actually, what happens is that things get rearranged because, and so this is the story that we had, like where we
Yeah.
were confused so much. If you don't pay very close attention to the ordering of your operations, you may mess up the memory profile. And so we looked at the literature, and there is some literature for having memory optimal computations. And that would, of course, be awesome, right? Having a memory optimal computation as is. But so it turns out that in a few places in Thunder, we are treating the computation not as a straight line program, but as a graph, and then we construct a new straight line program by doing a topological sort. So every like prerequisites, all the inputs will be calculated before the operation
Like
is
cross
done,
everything.
which
So
you need.
yeah.
But so these reorderings, apparently there's some paths that like does a not so good reordering, and we need to fix this yet. We fix it in a couple of places, and the checkpointing gives you like a relatively natural ordering here.
Yep.
But we still like have some homework to do to really, really fix the ordering in the later passes.
Yeah. So
We
bottom
want
line,
we
yeah, go
want
ahead.
this here more than we want the other one, right? I should probably just have this
Yeah.
here for
So
both.
as a bottom line, like what is the take-home message for this is that, well, first of all, memory is really important. Memory has effects on forward but on backward that are very, they can be limiting to your ability to train on a certain hardware. And the more control you have on memory, as we're doing right now, and the more possibilities for visualizing what's going on in your model you have, the more countermeasures you can take. And so right now, we also are hacking what would be normally something that happens within like deep down in a compiler. But in fact, what we're doing is just doing everything on a notebook because we have super fine grained control. So Thunder exposes a lot of what would be internals to the outside. So we have hooks and transforms that we could write in order to improve the situation directly, right? So that's what makes it very approachable. Well, relatively approachable, as approachable as it could be, I guess, to reason about memory in this way.
Yeah. So currently we have this like relatively high memory peak, and you can run it through the PyTorch memory tool too to inspect it, and we want to get to a lower profile.
Yeah.
And so this will be after Christmas in the next year. We will see how far we got for that.
So flatten the memory, because the more we flatten, the larger models we will be able to run on the same hardware, which is great. Or the smaller GPUs will be able to afford for the same model. So thanks a lot, Thomas. It's been absolutely a blast.
Yeah.
This year has been fun to see Thunder grow, and we're looking forward to do probably the next episode or the one after the next together. We'll have a mini retreat where we'll work a lot on the repository, set up examples, recipes, the READMEs. And so we're preparing for making Thunder more and more approachable. So 2025 will be a very nice year for Thunder. And so, thanks a lot for everything.
Yeah.
All the best for your break. Get a rest. Yeah. Don't think about memory.
Also, for viewers out there, you have a good break too, and see you next year.
See you. Thank you. Bye.